Hello everyone. This is a continuation of our series on motion in a plane where we were talking about projectile motion. So let's solve some problems on projectile motion before we move to the next topic. So here is the problem on projectile motion. The problem states that a ball is projected from a point on the floor with a speed of 15 meter per second and an angle 60 degree with horizontal. Will it hit a vertical wall 5 meter away from point of projection and perpendicular to plane of the projection without hitting the floor? Right. Okay. So let's say this is my point of projection, right? And I'm projecting this projectile at a speed of 15 meter per second and angle 60 degree with respect to horizontal, right? And the problem states that I have a vertical wall which is 5 meter away from this point. Let's say this is 5 meter and there I have something like some wall, some vertical wall is there, right? So the problem is asking whether this projectile will hit this wall or not, right? So projectile will take some trajectory, right? This might be the trajectory. So we need to find whether it will hit the wall or whether it won't be able to reach till this wall, right? There are only two possible cases, right? Either it will go and hit this wall or either it will fall back somewhere on this ground before coming to this wall itself, right? So So considering these two scenarios, we need to find whether this projectile will hit this wall or not, right? So two scenarios are the projectile will go and hit this wall, or either the projectile will go and fall somewhere before the wall. So it is not able to reach that particular distance. So these are only two scenarios. So we need to find what? We need to find the horizontal range, right? If we are able to find the horizontal range, we will be able to appreciate and understand this problem, whether projectile will hit the wall or not, right? So analytically, if we say that if range is greater than 5 meter, this projectile will hit the wall, right? Since range is more than 5, there is a chance that projectile will hit the wall, right? But if range is less than 5 meter, right? So projectile will land somewhere on the surface or the floor. It won't be able to reach the wall itself. So projectile will never hit the wall in this case. So everything comes down to finding the range now, right? So the very simple expression to find range of this type of projectile motion. This is the oblique projectile motion. So oblique projectile motion, the range expression is u square sine 2 theta by g, right? So if I place all the values, this becomes 15 into 15. This sine 120 by 10. This is the expression, right? So 15 into 15 into, let's say this becomes root 3 by 2 into 10. So this is 225 root 3 by 20. You will be able to find the answer. The answer is somewhere more than 20. So if it is more than 20, it is obviously greater than 5. This range is greater than 5 meters. And hence, this projectile will obviously hit this wall, right? But if I take this wall away from this distance, right? If I take this wall away and let's say place it somewhere at 30 meters. If I place this wall somewhere at 30 meters, the projectile will not hit the wall because it will come down and land somewhere at this 20 meters itself and it won't hit the wall, right? So the question can be given both the ways, right? So this is another problem on the projectile motion. The problem states that find the average velocity of projectile between the instant it crosses half the maximum height. Initial velocity is u at an angle theta, right? So when we talk about average velocity, we talk about two instances. One is initial, one is final, right? So there will be two instances where this projectile will be crossing the max of its height, right? Let's understand diagrammatically how. So this is my point of projection, right? And let's say this is my axis. So I'm projecting at an angle u, sorry, at an initial velocity u and angle theta, right? And let's say this is the trajectory of this projectile. This is the trajectory, and this is somewhere, this is my max height, right? Half of max height will come somewhere over here. Let's say this is h by 2 and this is also h by 2. So now you can easily relate that there are two instances. Let's say this is T1 instance and this is T2 instance, where the projectile was at half of its maximum height. And between these two instances, we need to find what is the average velocity. Okay. When we talk about average velocity, what is the definition of average velocity? Average velocity is net displacement by time. Displacement in that interval by time, right? So final displacement minus initial displacement by time, right? This is average velocity. And also this is, let's say, v1 plus v2 by 2, right? Which is sum of velocity at this instant plus this instant taken together divided by 2. This is what we call average velocity. So now this is motion in a plane. So at any point we will have velocity in two direction. Both the direction will have velocity, right? So let's understand that initial velocity along x direction is u cos theta and y direction is u sin theta. So at any point, we know that in a projectile, initial velocity is, sorry, the horizontal velocity is always constant because there is no force along horizontal, there is no gravity, there is no other force also, there is no acceleration, and hence u cos theta will be velocity at any instance if you take in the horizontal direction, right? The vertical component will change. But here, if you see one thing, if this is my xy axis, this point h by 2 and h by 2, they are at same level if you see vertically. So the y coordinate for these two points t1 and t2 are exactly same. So net displacement along y direction between these 2 points is 0. Displacement is 0 between these two. When we talk about average, we are not bothered about what is happening in between. We are bothered about what is initial and what is final. What is the status at initial, what is status as final. So so at initial and at final, at both the points, displacement is exactly the same point. So there is no displacement, right? There is no change in displacement. So if I talk about average velocity in y direction, average velocity in y direction, this becomes displacement by time, which is 0. In y direction, the object has not displaced at all between these two intervals, if you see. What about x direction? X direction, there is a displacement. So initially it was at, let's say, a point, now it is at b point, right? So there is a displacement along x direction. So for ease, we can easily calculate average velocity along x direction because we know at a, the average velocity along x was u cos theta, right? At a. And at b also, average velocity along x is u cos theta because the velocity along x is always constant since there is no force and hence no acceleration. So average velocity will become vxa plus vxb by 2, which becomes u cos theta along horizontal. So net average velocity, if you take between these two intervals, is u cos theta along horizontal. There is no average velocity along y direction because it is at same level vertically. So next topic for us is relative motion, right? So we'll talk about relative motion in 1 dimension and 2 dimension both together here. So the topic is relative motion. So this is nothing new. This topic we have already discussed if I talk about theoretical part of it. So we say that rest and motion are relative, right? Rest and motion are relative. What this exactly mean? This basically means that rest and motion, these two terms are very relative to the reference frame or what we call as observation point or we call as reference point, right? So based on observer, the rest and motion states are defined, right? So let's say if you are in a bus, let's say this is a moving bus, you are inside a moving bus, right? So you are sitting somewhere and there is one more passenger over here and there is another passenger outside. So we discussed that for if you are, let's say you are A and this person is B and this person is C. So according to person B, you are always at rest. You are not changing your position. But for person C, at every instant you are changing your position and hence for person C you are in motion, but for person B you are in rest, right? Hence we call that rest and motion are relative, right? But let's take one instance where we say that there is one more bus parallelly and there is person C inside this bus now, right? There is a person C inside this bus, and this is also moving forward, this is also moving forward. So now the observer, let's say person C is my observer or reference point, he is my reference point or he is my observer. So with respect to person C, now whether I'm in rest or motion, I don't know. Now it depends on how fast this bus is moving and how fast this bus is moving, and based on this two only, I'll be able to say whether for person C I'm in rest or motion, right? So here the frame has changed. Here the frame has changed. Now the frame is in motion. So if frame is in motion, I can't directly predict what is gonna be my state, right? Okay, let's understand by one more situation. So let's say there is a person walking on a street by 10 meter per second. What this exactly mean? What is this 10 meter per second? With respect to what it has a speed of 10 meter per second. So this person has a speed of 10 meter per second relative to ground reference, right? Ground reference. Ground, which is a stationary reference. So for ground, with respect to ground, this person has a speed of 10 meter per second, right? But if this person meet another person which is moving at 5 meter per second, so with respect to this person, it is no more at 10 meter per second, right? Relative to this person, the velocity of this person is not 10 meter per second. This 10 meter per second is its absolute velocity with respect to ground. So in ground frame, it has velocity 10 meter per second. But in person B frame, I don't know what is the velocity of this particular person. This will obviously not be 10 meter per second, right? So here relative velocity becomes more important. When we change our frame, right? When we change our frame of motion, how do we find that what is the relative velocity? How fast a person or a body is moving with respect to another moving body? So when we talk about these two quantity, these two terms, we talk about relative motion, right? So now let's find out what is the velocity of person A with respect to person B. Velocity of person A with respect to ground reference is 10 meter per second. Velocity of person B with respect to ground reference is 5 meter per second. But if we need to find the velocity of person A with respect to person B, we need to do something more. So we know that if frames are stationary, right? If frames are stationary or if the frame is at rest, I'll be able to calculate my parameters very easily. The calculations are very simple because I already know quantities for ground reference. So if I make other reference also as stationary, I'll be able to solve this dilemma, right? So if this person is moving at 5 meter per second and I need to make this person to rest, right? So what I will do, I'll take opposite 5 meter per second to this person, right? I'll take opposite 5 meter per second in the opposite direction, and same I'll do to this person as well. So what is the net velocity of this person now? Person A velocity is 10 forward, 5 backward. So net velocity will be, resultant velocity will be 5 meter per second in the forward, 10 minus 5. So velocity of person A with respect to person B is 5 meter per second in the forward direction or positive x direction. So how do we came at this conclusion? We made our frame of reference stationary by applying an opposite vector to it, and same we did at the our source also or the person where I'm calculating, and hence I'm able to find the relative velocity of person A with respect to person B. So as of now I talked about just the velocity, but there can be more terms. There can be a acceleration as well, there can be position, there can be anything. So generally if I talk about relative velocity or relative position of any vector, let's say relative velocity of a vector with respect to b is always given by what? Relative position vector of a minus position vector of b. So position vector of a with respect to b is given by position vector of a minus position vector of b. Let's understand graphically. So this is point A and position vector A, RA. This is point B and position vector RB, right? Now, this vector is RAB, which is position vector of A with respect to B, and with respect to triangle law, you can easily say that this is nothing but RA minus RB, RA minus RB, right? So now you can easily say from this that position vector of A with respect to B is given by position vector of A minus position vector of B. Very clear. Now let's say velocity, again differentiation of position vector will give me velocity. This will be v of A minus v of B. Acceleration A with respect to B will be given by A of A minus A of B. So what I am doing, I am actually adding negation of B vector to A vector here, same at all points. So when we are changing the frame of reference from a stationary to a moving frame, we need to reverse the vectors and add it to the original one, right? Like we just understood. Let's understand by one more example, right? Let's understand by one more example. So let's say this is a system, right? This is system, and there are, and let's say there is a surface here, right? This is some boundary, there is a surface, there is a person moving at 2 meter per second, right? There is a person moving at 10 meter per 2 meter per second. There is a cloud which is the rain is popping at, let's say, 10 meter per second vertically, right? And again, let's say there is some more body, maybe let's say one vehicle which is moving forward at 5 meter per second, right? Let's say this is the scenario, and these all velocity are in ground frame. So this is ground, so all these velocity are in ground frame, right? So let's say this is body A, this is body B, this is body C, right? So with respect to ground, body B is moving at 2 meter per second forward direction. Body A, sorry, body B, which is rain, is coming down at 10 meter per second vertically. Body C is moving at 5 meter per second in the forward direction. With respect to ground, now I am changing my reference. So let's say if I need to find with respect to C, with respect to body C, what is velocity of body A and body B, right? With respect to body C. Now, I told the best way to find this is by stopping this body, and same, and we'll do same for A and B as well. So if C is my reference body, I will make this body to stationary by doing an opposite vector of 5 meter per second, and now this is stationary. Now my frame is stationary. Same I will do to this also, and this as well, and resultant I can easily calculate for body A and B. So body A becomes what? Body A resultant will become 5 minus 2, which is 3 meter per second negative x direction. For this, for rain, net velocity of rain will come somewhere over here, which is under root 10 square plus 5 square. Angle you can also calculate, right? This is velocity of rain with respect to C, right? And by formula also, if you want to calculate, you know, velocity of A with respect to C will be what? Velocity of A minus velocity of C, right? So velocity of A was what? 2. Let's say if this is x-axis, let's say 2 I cap, and velocity of C was what? 5 I cap. So it is minus 3 I cap. So mathematically also we can easily calculate this, but by physics we can easily understand that if my reference is moving, if I'm moving from ground frame to a moving reference frame, the best method to find the relative quantities are, I'll apply opposite vector to this moving reference, I'll stop this, and same operation I'll do for others also and find the relative quantities, right? So let's understand by one more scenario. Let's say there is a track, and there is a train which is maybe moving at, let's say, 15 kilometer per hour, right? There is a train moving at 15 kilometer per hour, and simultaneously there is one more train which is maybe some 5 kilometers away, and this is moving at, let's say, 10 kilometer per hour. So now, if I need to find after how much time this train, let's say this is train A and this is train B. So after how much amount of time train A will cross train B completely, right? Okay, to solve this particular problem, right? To solve this particular problem, we need to go into the relative motion concept, right? Because here these two trains, these two are moving, right? These two are moving trains and they're moving in the same direction, right? They're moving in the same direction. So if I'm able to calculate the relative velocity of one respect to other, I'll be able to ease this particular problem. So let's not find out what is the answer and all that for now. Let's understand how can we find the relative velocity of one with respect to other when two bodies are in moving in the same direction, right? So I told that this 15 kilometer per hour speed is in the ground frame. So this is, let's say, ground frame, and velocity of train A with respect to ground is 15. I have written A comma G, A with respect to ground. So this is what, 15 kilometer per hour, and velocity of B with respect to ground is 10 kilometer per hour, right? Now we need to find what is velocity of train A with respect to train B, right? So first, whether this train will be able to cross train B or not. Analytically, let's find this, the speed is more for this particular train. The speed is higher. It is 15. This is 10. So obviously, at some point of time, this will cross this train, right? So now, velocity of train A with respect to train B. The best way to calculate is I'll go ahead and stop this train. I'll make my frame as stationary again, and then I'll be appreciate how do we make things, right? So this is moving 10 kilometer per hour in positive x, right? So what I will do, I'll apply at 10 kilometer per hour in negative x direction, right? So if I have done for this, I'll do for this as well. So now I can say the relative velocity of train A with respect to train B becomes what? So 15 in forward direction, 10 in opposite direction. So net will be 5 in forward direction, right? Easily I can calculate by vector method. These two are anti-parallel vectors. So net velocity of train A with respect to train B is nothing but 5 kilometer per hour. So this is VAB, which is velocity of train A with respect to B. This is 5 kilometer per hour in positive x direction, right? So now I have made this train as stationary. I can easily solve the problem now. So 5 kilometer is the distance and the length it has to cover. So I know distance by time is, so distance, I know the distance, I know the speed, I can find the time. Time is distance by speed, right? So now let's discuss the situation we just explained, right? So now I have given the values to all these lengths. So this is, let's say, train A, this is train B. Both trains are of length 5 meters, right? Both trains are, let's say, only 5 meters as of now. This is moving at 15 meter per second. This is moving at 10 meter per second. And the distance between these two trains are 4 meters. So this is explained diagrammatically. You can see everything. So now we need to find after how much amount of time train A will cross train B, right? Or overtake train B. This is an overtaking problem. So best way to solve any overtaking problem is using relative motion concepts. So now velocity of train A with respect to ground is 15. Velocity of train B with respect to ground is 10. But velocity of train A with respect to train B is 5 meter per second. We just find how. So VA with respect to B will be what? VA minus VB. Right. Vectorically we know this, but analytically also we can say that if we are about to find a velocity of one body with respect to another, we will take a reference body to rest by applying an opposite vector. So this is 10 in forward, so I'll take 10 in opposite. If I'm doing for this, I'll do for this as well. So this has net velocity 5 in the forward direction. So this has a net velocity of 5, but how much distance it has to cover? So to let's say this is the tip of this train. So when this train overtakes this train B, it has to be somewhere like this. It will look something like this. This is train A, and this is tip of train A. It is coming here, So how much distance it is covering? You see, it is covering this 4 meters. It is covering length of train B as well, and it is covering its length as well. So this much amount of distance it is covering to overtake this train B completely. Completely means there is no part which is overlapping now. So the net distance is 4 plus 5, which is distance is what? 14 meter it has to cover, and velocity, which is relative velocity, is what? 5 meter per second. Time is nothing but distance by speed, which is 14 by 5. You can easily calculate this is 2.8 seconds. So after 2.8 seconds, this train A will overtake train B easily, right? So let's solve another 2D problem in this topic, right? So what is relative velocity of rain with respect to moving man, right? So there is a man, so directions are indicated east, west, north, and south. So there is a person who's moving towards west with a velocity of Vm, right? The velocity of person is Vm and moving towards west direction. This Vr is velocity of rain which is falling vertically downwards at 90 degree with respect to horizontal, right? So rain is falling vertically at Vr, and the man is moving at velocity Vm to the west, right? So Vr is the velocity of rain with respect to ground, right? So if a stationary body is there on the ground, he or body will see the rain droplets coming vertically and falling on itself, right? So rain droplets will appear to fall vertically on it, right, till it is rest on the ground, right? But as the body starts moving, the rain droplets in this case will not appear exactly as falling vertically on him, right? Rain droplets will start coming at some angle because the body has also attained some velocity now. So velocity of rain or the nature of rain with respect to that body is changed now, right? So this is a kind of a rain man problem, right? So using this problem we can say that at how much angle I should hold my umbrella so that the rain won't affect me and makes me wet, right? Using this concept. So the concept is, for this particular problem, the rain is falling vertically, right? So till this man is at rest, the rain will fall vertically, and he'll also see that rain is coming vertically, and I can just hold my umbrella in the vertical direction. But now he has started moving in west direction with the speed Vm. So the velocity of rain with respect to man is no more this horizontal velocity which is Vr, right? So velocity of rain with respect to man has changed now. So what is that velocity? Right. Velocity. So I know what? I know velocity of man which is Vm. Right. Vm is velocity of man with respect to ground. And I know velocity of rain with respect to ground which is Vr. Right. I'm just let's say talking about only magnitudes as of now. Right. Directions you can easily say that this is in the minus j cap and this is minus I cap. Right. Minus x and minus y. Now, I need to find the velocity of rain with respect to this man, with respect to a moving man. So what I will do, I will apply opposite vector to this man and I'll make my reference stop, right? This is the best way to solve relative velocity. So I'll apply a Vm here in the opposite direction, right? And same Vm will apply for this rain as well, right? So now net velocity is resultant of Vr and Vm. Net velocity of rain with respect to man is resultant of this Vr and Vm, right? So what is the net velocity? This is under root Vr square plus Vm square. And if I talk about angle, tan theta will be Vr by Vm, right? So velocity of this rain with respect to man is tan theta, which sorry under root Vr square plus Vm square, right? And angle is Vr by Vm, right? So velocity of rain with respect to man, the magnitude of velocity is under root Vr square plus Vm square, and the angle is Vr by Vm. Now, if this man, so this man, for this man, the rain will appear to be coming at this angle and this velocity. So if he wants him to protect himself from this rain, at the same angle, he will hold the umbrella, to not get wet, right? So this man need to hold umbrella, let's say this is the umbrella, at the same angle to not get wet, right? So this angle with respect to vertical, let's say this is alpha, with respect to so becomes 90 minus theta. So with respect to vertical, this is 90 minus theta is the angle. So at this angle, this man need to hold his umbrella so that he does not get wet, right? So how, with respect to a moving reference, how these things are changing, you can easily understand that if rain is falling at a velocity vr and the man is stationary, the rain will appear coming vertically exactly at 90 degrees and he can hold umbrella in the same direction. But if the man starts moving, then we need to see that what is the velocity of rain now with respect to that man to calculate what should be the angle of his umbrella to get protected from the rain, right? So we'll solve more problems on this rain man problems and again river boat problems in the coming lectures, right? Till then, thanks.